Okay, this is me recording the video after the Zoom interruption. Um, I hope this recording goes well. So let's continue from where we left. I hope you can see. Um, so we are looking for this uh, particular satellite signal in the signal that we are receiving, that the GPS receiver is receiving. And we said correlation is a good idea whenever we are looking for similarity, whenever we're looking for a match. And the product of two signals is a good way to pattern match. Right? As we said, when they both go up together or they both come down, the product becomes positive. While if one goes up and the other goes down, the product is negative. Right? So correlation can be written as, let's say this is a K size signal that we are looking for. In this case, K equals 5. So it's K I equals 1 to K SI YI. Essentially taking the SI from here and the YI from here, and we just multiply, and that would mean you're essentially taking a dot product of the S signal with the Y signal that you're looking for, with the S signal that you're looking for and the Y signal that you're receiving. This is a dot product because look, this is SI, YI for every element in SI and YI is a dot product. Okay, good. Now, if YI is exactly SI, then great, right? Then it'll be a perfect match with whatever you are looking for. But in general, what happens is YI is nothing but SI plus NI, where NI is noise, and this is because of hardware noise. So what is hardware noise? Well, the idea is that when a signal comes in and when the signal gets sampled, first of all, the reception of the signal, if some voltage comes in, when the signal hits the antenna may not exactly be able to pick up the precise voltage. There might be errors over there, often depending on the temperature of things, the impedance mismatch of things, and so on. Further, when the signal is sampled from analog to digital, you may not be able to sample at the exact value. You might sample only at certain discrete values. So from the time the signal hits the antenna of the GPS receiver, or any antenna or any receiver for that matter, till the time when the signal comes out as digital samples, it is not preserving accuracy completely. There is some noise that is getting injected by that hardware. Okay? This is called hardware noise. So essentially what happens is your correlation now becomes S times Y, where Y is really some S plus N. That's your Y received signal vector. Right? And now if you do the correlation, what you essentially get is S squared plus S dot N. Makes sense, right? You're multiplying this S with this S first, plus this S with this N. Okay. So one way to think about this is, oh, your signal that is the GPS satellite is sending is S, there is some other noise vector, and what you're essentially getting is the signal plus noise, and that signal is what you're receiving, and you're correlating that signal with the signal template that you're looking for. Great. So now look at this one. If S square is much greater than Sn, then decoding is possible. Then you can say, yes, the signal is present. Right? But if S square is not too much greater, if S times N is pretty comparable, then it's not clear because that correlation value would be pretty low. Right? So thus S and N need to be uncorrelated That is, expectation of S and N should be 0. Right? The S vector dot product with the N vector in expectation, although noise is random, so it's not like one deterministic vector, it can come from many directions, it can come in many directions, but in expectation that should be 0, and this correlation value should be 0 so that the S square value dominates this signal. The S square value dominates in this correlation. Great. So in practice, how will K impact the correlation value? K being the size of the signal. Think about that for a second. If you want the signal to be better visible after the correlation, should this signal template be longer or shorter? If it is shorter, then this S square and this Sn are likely to be close to each other, because the N is basically pulling you away from matching the signal well. But if you have a long one, this S times N over a long signal is more likely to converge to 0. And therefore, this S square would become more and more dominant compared to S times N. So if you have long signals, that is better for correlation. And as a result, you can say that larger the K, better is decoding. In another way of thinking about this is, instead of saying Alexa, if you said, hey, Mr. Alexa from Amazon, right? Suppose you have to say that, hey, Mr. Alexa from Amazon, and then say your voice command to Amazon Echo. That would be much better, right? Echo would be able to exactly figure out when that sentence is being said, because the correlation is much longer. But again, it's painful for humans. So that is why Amazon designed it as Alexa. It's a quick one, but it's a short one. So that correlation is harder. Very good. So now we detect the presence of S in the GPS signal, but that is not enough, right? Since it's not enough because since I also need to decode the time of arrival, right? This is something Alexa does not have to do. I mean, Amazon Echo doesn't have to do, right? But GPS signals have to do, right? So now this is a problem, because if the satellite signal changes very slowly, then S will also match well with a shifted version of Y. Right? Suppose the satellite signal, which is Y, is changing very slowly. Or think of it the other way. The satellite signal is changing very fast. This sample it's positive, next sample it's negative. Right? So now with this Y, if you match S, if you shift the signal a little bit, the matching will be really bad, because sample number 1 was positive, sample number 2 was negative. So when you match it exactly, S and Y would be coherently adding up, right? Positive will add up with positive, negative will add up with positive multiplied by positive, negative multiplied by negative, everything will be positive. But instead of that, if the signal Y from the satellite was changing very slowly, then even if you shift S on Y, the correlation value is not going to change much. So in other words, S of N minus J should not match well with signal Sn, right? So the satellite signal should be such that if you take that signal and if you shift it and match, that matching should be bad. But if you take that signal and you exactly align it and match, that matching should be great. And that matching will always be great. Right? So in some sense, we are saying S should show very bad match when, okay, let me write it this way. Matching S with S shifted should be very bad. Right? Matching S with S shifted should be very bad, but matching S with S is obviously pretty good because that's exact matching. Right? This is called good autocorrelation property. Okay. So ideally, the expectation of Sn and Sn minus j should be 0 for all j not equal to 0. What is the expectation of Sn and Sn minus j? For all possible Sn and all shifted values of Sn, if you take that dot product where the shift can be shift by 1, shift by 2, shift can be for any value of j, for that Sn and the shifted value of Sn, that product in expectation should be 0. Right? These are good autocorrelation signals. So the satellite should send signals that have good autocorrelation property. That means if you take a shifted version and if you multiply, that should have a very low value. So quickly, maybe here is an example. 10111010. This, if you multiply it with a shifted version, if you multiply this, this is, let's actually bring this 0 back here. So this is 0, 0, 0, 1, 0, 0, 0, which is, if you add them up, if you add them up and you divide by 1, 2, 3, 4, 5, 6, 7, so this is equal to 1 by 7. Right? So this is a signal which has pretty good autocorrelation property, right? Because you've shifted and the signal has gone down dramatically. If you did not shift, the signal would be, the value would be much higher. Right? Actually, maybe we should do it this way. Yeah, I think actually we should do it this way. Yeah, maybe 6 values. And let's do this 1 minus 1, 1 minus 1 minus 1. And now we have 1. Right? And now let's do the product. Let's bring the 1 here. So now it becomes 1 minus 1 minus 1, 1. Sorry, minus 1, 1, minus 1. Right? And now we sum this up and divide it by 6. So this is basically 1 minus 1 cancels, minus 1, 1 cancels. It's minus 2 by 6, which is minus 1/3. Right? Whereas if you aligned it and multiplied, it would have been 6 by 6. When aligned, it is 6 by 6, which is 1. Right? So this is a reasonable autocorrelation where it dropped from 1 to minus 1/3. Right? But now look at something that has bad autocorrelation. That might be like this: 1, 1, 1, minus 1, minus 1, minus 1. And now you shift that 1, 1, 1, minus 1, minus 1, minus 1. You bring this over here. And now you take the product. Minus 1, 1, 1, minus 1, 1, 1. Okay. So this minus 1, this one cancels. This minus 1, this one cancels. So now you have 2 divided by 6. Okay, so this is still not too bad. This is still not too bad because this gives you 1/3. But remember, this was minus 1/3, and this is 1/3, and this 1/3 is much better than minus 1/3, right? Because we said that autocorrelation, higher the value, better it is. Lower the value, the signals are dissimilar. Okay? So this is a case of not so good autocorrelation property. I hope you get the point. Okay. So satellite signals need to satisfy this property, that it needs to have good autocorrelation property. Finally, there is one more condition. You know, signal Z that is expected from other satellites should exhibit poor cross correlation to S, which is coming from satellite 1. What am I trying to say? Suppose satellite 1 is sending S, satellite 2 is sending Z. Okay. Now I am trying to look if satellite 1 is within my view, within my audible range. So I take satellite S's signal S, which is this. But suppose satellite 1 is not in my view, but satellite 2 is. So if this S matches with Z, then I will incorrectly infer that satellite 1 is in my view. Right? So in other words, if this is satellite 1 and this is satellite 2, and satellite 1 is sending S and satellite 2 is sending Z, if I match satellite 2's signal with Z, if I match with Z, this Z should not match with S. That means the correlation between Z and S should be very small. The correlation between Z and Z will be high, but the correlation between Z and a shifted version of Z should be very low. These are the properties that the signal needs to satisfy. If this cross correlation property is not satisfied, then otherwise Z will match with Y and GPS receiver will detect the wrong satellite. That you don't want, right? So in summary, 3 properties are necessary for the satellite signals. The satellite signal should satisfy 3 properties. 1, it should be uncorrelated to noise. Right? 2, it should have good autocorrelation properties so that I can figure out, detect timing. Okay, detect timing of arrival. Uncorrelated to noise means I will be able to correlation will work with weak signals. Remember, satellite signals are weak. So correlation will work with weak signals, work better with weak signals. Good autocorrelation means detect timing of arrival, and weak cross correlation means no confusion with wrong satellite. Right? So satellite signals should be designed with 3 properties in mind so that at the end, the GPS receiver knows which satellite is there through correlation. Even though the signal is weak, it can figure that out and knows the timing of the signal's arrival and does not get confused by other satellites. So because of this, GPS uses CDMA codes, and these CDMA codes satisfy these three properties of the signal, and that is why you can detect the signals well, get your TR, which is the reception time, decode that well, and of course, your time synchronization delta is still unknown. That can be anything, that can be arbitrarily large, regardless of whether you do these things well. But if your TR is good, then every time you decode the satellite signal, you will consistently decode it correctly. Otherwise, there are problems. Okay. I hope this explains the whole scenario around GPS localization. We will stop here and we will continue with Wi-Fi based indoor localization next class. But I'm glad I could finish this video. I'll upload this as a part 2 of today's lecture, and we will take it from there. Okay, and you'll have the opportunity to ask questions about this when we meet on Monday. Okay, thanks for listening to this, and I'll see you again on Monday. Okay, bye.